students, welcome to the video lecture series on Chemical Engineering Thermodynamics 2. I am Jamin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter number 3, which is Chemical Reaction Equilibria. So in this lecture, we are going to discuss about the standard Gibbs free energy change. In previous lectures, discussed about the equilibrium constant. Equilibrium constant that denoted by K, that given by capital Pi AI Vi. What is meaning of capital Pi? As meaning of sigma AI, which means A1 plus A2 plus A3 and so on. Similarly, we can write capital AI, which means A1 into A2 into A3 and so on. Okay, so this is meaning of the pi. Now what is A? A is the activity of component I, and what is Vi? Vi, which means stoichiometric number for particular component I. And what is meaning of activity? Activity is the relative fugacity, so can say that Ai is equal to Fi bar upon Fi naught. Okay, so replacing this activity with relative fugacity, so we will get capital Pi of fugacity in solution upon fugacity of particular component I at standard state whole raised to this Vi. So this is the equilibrium constant, which denoted by capital K in term of the activity and in term of the fugacity. Now let's discuss about the standard Gibbs free energy change, or can say that delta G is equal to minus RT ln K, which is the most important equation for point of view of exam and in point of view of chemical engineering thermodynamics too. So we are going to prove this equation. So let's first discuss about the standard Gibbs free energy change. Standard Gibbs free energy change that denoted by delta G naught is equal to minus RT ln K. Okay, so in exam this question asks like prove that delta G is equal to minus RT ln K, or also in exam asks that prove that standard Gibbs free energy in term of the equilibrium constant. So we have to first to prove this, first we have to consider the fundamental property relation for the chemical potential that can be given by del GT is equal to VdP minus SdT plus summation of mu I d Ni. Okay, now we already proved dni is equal to Vi d epsilon. So replacing this dni with Vi d epsilon, this equation becomes dgt is equal to Vdp minus SdT plus summation of mu I Vi d epsilon. Okay, at equilibrium we already proved that at equilibrium Gibbs free energy is a zero. So let's suppose at equilibrium where temperature is a constant and pressure is a constant, this term becomes zero at constant temperature and constant pressure, and Gibbs free energy which also becomes zero. So can say that summation of mu I Vi d epsilon is equal to 0. So can say that summation of mu I Vi is equal to 0. So let's consider this is our equation number 1. Now from definition of fugacity we can write mu I is equal to RT ln Fi bar. At standard state Gibbs free energy that can be given by T naught is equal to RT ln F naught. So let's consider this is our equation number 2 and this is our equation number 3. So subtract this equation number 3 from this equation number 2, we will get mu I minus G naught is equal to RT ln Fi bar minus RT ln Fi naught. Okay, so mu I minus G naught is equal to, taking RT common, it becomes ln Fi bar minus ln Fi naught. So I can write mu I minus G naught is equal to RT ln Fi bar upon Fi naught. Now let's consider this is our equation number 4. Using value of mu I from the equation number 7, or sorry, from the equation number 4. So if I am going to use the value of this mu I from this equation number to find out this value, I have to write mu I is equal to, taking this Gibbs free energy to this side, so it becomes value of mu I. So it will be a minus Gi. So if I am going to take this side, it become positive, plus RT ln Fi bar upon F naught. So plus RT ln Fi bar upon Fi naught. So let's write this is our equation number 5. Now putting value of this mu I of equation number 5 in this equation number, or putting this equation number 1. So if I am going to put that value in this equation number 1, then can say that summation of Vi, okay, so it's Vi not mu I, so Vi into mu I. So this is our equation number 1 in this Vi, and we have to put the value of mu I. So if I am going to put the value of mu I, it becomes G naught plus RT ln Fi bar upon Fi naught is equal to 0. Okay, so this equation number 1 becomes like this equation number 6 or equation number 5. Now then again rearranging this equation. So now rearranging this equation, which becomes Vi G naught plus RT summation of Vi ln Fi bar upon Fi naught is equal to 0. So summation of mu I, or can say that Vi G naught plus RT summation of, taking this ln to this side, or taking Vi to upper side, so it becomes summation of ln Fi upon Fi naught whole raised to Vi, us using logarithmic law. Okay, so I can take this Vi to power of this. Okay, so this equation becomes like this. Now I am replacing this summation of ln Fi upon Fi with capital pi, so it becomes ln pi Fi bar upon Fi naught is equal to summation of Vi naught upon RT. So why I am writing this capital pi here? Because summation of ln Fi bar upon Fi naught. Okay, what is meaning of this? Meaning of this, ln Fi plus Fi naught plus ln Fi plus Fi naught. Instead of I, there will be 1, 2, 3 and so on. So as using the logarithmic law, I can write ln Fi into Fi, F1 upon F1 into F2 upon F2. Similarly, F3 upon F3. Here there is a bar, and here there will be a standard state stochastic. Okay, so for this I can write ln pi of Fi bar upon Fi naught. So that's why here I write capital pi instead of this sigma. Okay, so this equation becomes like this: ln pi of Fi bar upon Fi naught is equal to summation of minus summation of Vi Gi naught upon RT. Okay, so this equation becomes like this, where the significance of pi, which I already told you, the significance of capital pi, which is the product of overall species of I. Now, in previous lecture, discuss about pi of this term, or can say that pi of Fi bar upon Fi naught is equal to our equilibrium constant K. So can say that ln K is equal to, and meaning of minus summation of Vi Gi naught is equal to delta G minus delta G naught. So it becomes minus delta G naught upon RT. Okay, so this becomes our equation for standard state Gibbs free energy change. If I am going to simplify this equation again, so it becomes K is equal to e raised to, or exponential whole raised to, minus delta G naught upon RT. Or we can also write this equation like this: delta G naught is equal to minus RT ln K. Okay, so taking this RT to this side and minus to this side, so it becomes delta G is equal to minus RT ln K, which is the most important equation in point of view of exam, and it's also important in chemical engineering thermodynamics too. So let's again revise how we prove this equation. To prove this equation, delta G is equal to minus RT ln K, first we write fundamental property relation for chemical potential. So this equation already derived in chapter number 2. So at constant temperature and pressure, this term becomes cancelled, and at equilibrium, Gibbs free energy is 0. So write 0 here. So this equation becomes like this. Taking this d epsilon to this side, so it becomes summation of mu I Vi is equal to 0. In this fundamental property relation, we are replacing this dni with Vi d epsilon, which already proved in before 2 lecture. So this replacing this Vi d epsilon instead of dni, then again we are putting the value of this here, then simplifying this equation, we will get this equation number 1. Then write from definition of fugacity value of mu I, because I just want to put the value of mu I here, that's why I am writing the mu I is equal to RT ln Fi bar. Then write the G naught is equal to RT ln F naught. Change in from standard state, because here our question is that the standard state Gibbs free energy, so I cannot only use mu I have to subtract this G naught from mu I to find out the value of mu I. So I am just subtracting this G naught from mu I, so it becomes RT ln Fi bar. Simplifying this equation, I will get this equation. Now using this equation, taking this G naught to this side, I will get value of mu I. So putting the value of mu I in this equation number 1, we will get this type of equation. Simplifying this equation, we will get delta G naught is equal to minus RT ln K. So this is how we can prove the delta G naught is equal to minus RT ln K. So this is all about today's lecture. I am completing my lecture here. Thank you.